Yeah, my name is Adele Zawada. I'm from Stanford University, and I'll report on our slow light FPG pressure sensors that have record-breaking resolutions. So first, I'll do a very brief background on FPG pressure sensors. So a Fiber-Bragg-Grating is a silica fiber where the core is, the index is modulated in the core over a very short length. If you look at the transmission spectrum as a function of the input wavelength, you get a band gap on the order of about a nanometer. And the wavelength at which this minimum occurs is called the Bragg wavelength. If you apply a pressure wave to the silica fiber, the core is going to elongate, and that's going to change the spacing lambda, which will then shift the Bragg wavelength. So this can be turned into a pressure sensor if you have a probe wavelength that interrogates the edge of the band gap. And when the pressure wave is applied, the spectrum will shift by some delta lambda, and the transmission at your probe wavelength is going to change. So if we think about a sensitivity of such a device, it's defined as the change in transmission due to an applied pressure dP. You can deconstruct this sensitivity as the product of two different parameters. The first parameter being the slope of the transmission spectrum, and the second parameter being the pressure-induced wavelength shift, or d lambda dP, so how much your spectrum shifts due to an applied pressure. So in this talk, I'll talk about how we improve the resolution of our devices by enhancing each of these parameters independently. So the first improvement we make is by using a steeper slope using slow light. So a slow light FPG is different than a conventional FPG in that the index modulation is much more strong, and it also has a different shape rather than just being uniform. So the result is that you get these very narrow spectral resonances near the edge of the band gap. And so the one that we use is this one here, and it has a slope on the order of 10 to the 12 inverse meter, which is exceedingly steep, especially if you compare it to the edge of the band gap slope here. So that's how we enhance this first parameter, dt d lambda. The second parameter is the pressure-induced wavelength shift, and that's a bit harder to control. The reason for that is that it's mostly controlled by the material properties of silica. And unfortunately, silica is nearly incompressible, meaning that even if you apply a large pressure to the fiber, the core is not going to stretch by that much, and the wavelength shift isn't going to be significant. So even if you have a very steep transmission slope, if this parameter is small, your sensitivity is going to be small. So one way to get around that, or a possible solution, is to coat your silica fiber in an elastic material, as depicted in this figure. So if you have an elastic material that's more squishy, it's going to transfer significantly more axial and radial stress to the fiber when a pressure wave is applied to your fiber, your coated fiber, and that's going to give you a better resolution, or a larger pressure-induced wavelength shift. So this was proposed by Hawker in 1979 and tested experimentally by Mocha in 2012. And in particular, Mocha reported that when they coated their silica fiber in a polyurethane demi-vol, they reported an enhancement of a factor of 300. So these are very promising results that we wanted to test with our slow light FPGs and see if we could get a similar enhancement. Our experimental setup is shown here. We have a laser that is launched into our slow light FPG. We have a calibrated microphone directly next to our FPG that measures the absolute pressure incident on our grating. These sensors are both placed in an acoustic chamber to isolate it from the lab acoustic noise. We also have a speaker inside the chamber where the amplitude and frequency of the applied pressure wave is controlled by a function generator. The output of our slow light FPG is measured by a photodetector, and that modulated signal is sent to a digital spectrum analyzer to extract the amplitude of the modulated signal. So one example of such a time trace is shown here. So this is when the speaker has a pressure wave of 730 hertz. We have two curves. The first is the blue curve, which is the reference microphone output power as a function of time. And then the red curve is showing the FPG microphone output power as a function of time. So this red signal is read by the photodetector, and then the DSA extracts the amplitude of that, and that gives us a measure of the sensitivity. So it tells us how much our transmission is changing for an applied pressure, which is measured by our calibrated microphone. Then what we do is we turn the speaker off, and we measure the noise, also recorded by the DSA, over the same frequency range that our acoustic measurement was measured. And then finally, we calculate the minimum detectable pressure, which is the noise divided by the sensitivity and normalized to the input power. And this is a very normal parameter to characterize pressure sensors. So the third and final improvement we made to our sensors is noise reduction. So to enhance the performance of our devices, I talked about how we increase the sensitivity S, but you can also improve the performance by lowering the noise. In these sensors, the typical dominant noise source is the laser frequency noise, and that's can be explained by this diagram here. So this is a picture of one of those spectral resonances that we interrogate with a laser at the probe frequency. However, the probe frequency isn't perfectly stable. It has some fluctuation in the frequency, as shown by this red line. And that frequency fluctuation is translated into an amplitude fluctuation, which is a big source of noise, especially if you have a very steep resonance like we have. So the way we get around this is by using an ultra-narrow line width source. Our line width is on the order of 90 hertz. And when we measured our noise, we are actually dominated by detector noise at a frequency for acoustic frequencies over 500 hertz. So now I'll present our results. So first, this is when our slow light FPG is in air. I'm showing the minimum detectable pressure as a function of the acoustic frequency. So first, the green curve is when we measure the bare slow light FPG. And then when we coat that same bare FPG in the demi-vol coating, we measure the purple curve. So the first thing to note is that we do get enhancement in the performance by about a factor of 16 over the entire frequency range. The next curve to look at is the black curve, which is the previous record for a passive fiber microphone, and it held the record for a very long time. It was measured by Loveseth in 1999, and you can see our purple curve is better than that previous record by an order of magnitude over most of the frequency range. The blue dots are measured by our group in 2016, and we're the first ones to break the record for the DFB laser. Our coated microphone measures better than that by about a factor of 6 over most of the frequency range. So then when we perform these same measurements underwater, we get these results. So our bare fiber is shown in blue, and then after we coat that bare fiber in the demi-vol coating, we measure the red. So here the red curve is about 23 times better than the previous record over the same frequency range from 4 to 35 kilohertz. And we also do see an enhancement from going from a bare fiber to a coated fiber, but this enhancement is smaller. It's only about a factor of 3.7 improvement. And it's important to note that this factor of improvement is markedly different than the factor of 300 that was reported by Mocha et al. So to understand where this discrepancy is coming from, I'll share what Mocha et al. Presented in their paper. So this plot is showing their responsivity gain as a function of the acoustic frequency, where the responsivity gain is defined as 20 log of the ratio of their measured coded sensitivity divided by the sensitivity of a bare FPG. But here, they did not measure the sensitivity of the bare fiber. Instead, they used the theoretical value, which is given in this equation here. It's a very well understood equation. It's just dependent on the material properties of silica for how much wavelength shift you get for an applied pressure. And so this is the source of the discrepancy. So if we plot these results and directly compare them to what we measured, we get this plot here. So now I'm plotting the pressure-induced wavelength shift as a function of the acoustic frequency. So our results are shown in blue for bare, coded for red, and then overlaid is the results from Mocha et al. And then finally, I've plotted the black dashed line, which is the hydrostatic limit, which is the value of the equation I showed on the previous slide. So the first thing to note is that we have very good agreement with Mocha et al., meaning that there's a good agreement on what the pressure-induced wavelength shift of a demi-vol coated FPG hydrophone is. The second thing that this plot shows is exactly where the discrepancy is arising from. So when we calculated our enhancement factor, we were comparing the measured sensitivity of our coated to that of our measured dynamic sensitivity of a bare. fiber, whereas Mocha et al. Was comparing their measured coated fiber to that of the theoretical limit of a static fiber. So this was not measured by them. So I want to highlight that there's nothing wrong with the way that Mocha et al. Presented their results, but perhaps it's more fair to, when characterizing the enhancement factor of a coated fiber, to compare that of two fibers that are performed under the same exact experimental conditions. This plot also highlights a new discrepancy, which is that there's a factor of about 80 between what the theoretical limit of the sensitivity of a bare fiber is to that of what the measured dynamic sensitivity of a bare fiber is. This is not the first time that this has been observed. LeBlanc reported these results in 2000 and was unable to resolve this discrepancy as well. So one possible solution is that when we do a dynamic measurement of the sensitivity and apply a pressure wave to the fiber actually vibrates, and that induces additional phase shift in the fiber to enhance the sensitivity. So to test this theory, we decided to try and immobilize the fiber from vibrations and then redo the measurement to see if we could reach this static limit. So here are some pictures of our setup. So the first one is when we have a free bare FBG hanging between two rods where it's allowed to vibrate. The fiber is right here. Then the second measurement we did was using that same grating. We sticky taped it to a large metal block to prevent it from vibrating and perform the same measurement. So in air, these are our results. So we have the free bare FBG in orange, and then we immobilize the fiber and measure the green curve. And then the static limit is shown in the black dashed curve. So we do see a reduction in the sensitivity from immobilizing the fiber from vibrations, but it's not yet to the static limit. When we perform the same measurement underwater, we get these results. So again, free fiber is shown in orange, and then immobilized is shown in green. Above a kilohertz, there's a factor of about 3 reduction in sensitivity after fixing the fiber. But again, we're not at the static limit. The reason that there's a lower reduction in sensitivity for the hydrophone case is that water is more dense than air. So the free fiber is already vibrating less in water than in air. So there's just fewer vibrations in this orange curve. So in conclusion, we report record-breaking resolutions for a passive FBG pressure sensor, a factor of 6 better than the previous record for microphone and 23 times better than the hydrophone. We also show that coating the FBG does improve the sensitivity of the device, but not by as much as previously reported. And finally, we have an unresolved discrepancy between the static and dynamic sensitivity of a bare FBG. We've tried immobilizing the fibers to reduce the vibrations, and that didn't reach the theoretical limit. So there's still an open research question as to why we have a larger dynamic wavelength shift. Thank you.